Good afternoon friends. Last time we discussed about Hilbert transformer. Today we shall be taking up multi-rate signal processing. What is this multi-rate signal processing? Now, so far we have used both the input and the output frequencies of any system, that is the sampling frequencies same. If this is sampled at 1 kilohertz, output is also obtained at 1 kilohertz sampling frequency. Okay. So, the sample points were at regular intervals, at the same intervals both at the output and the input. Sometimes we are working on systems where there are say signals coming from different places which have been sampled at different rates, and we want to put them together. We are required to convert the frequencies, sampling frequencies, from one value to some other value, and that need not be always a submultiple or multiple of the existing sampling frequency. For example, suppose you have sampled at 2 kilohertz and now you are required to give a signal with 4 kilohertz or maybe half of that 1 kilohertz. Then what do you do? Under what conditions you can have a different sampling rate? Are there any restrictions? This is what we are going to see, and if at all we want to change the sampling rate, how do you do that? Now, as I told you, from 1 kilohertz you can go to 2 kilohertz, you can go to 500 hertz just by dividing or multiplying by 2. Suppose from 1 kilohertz we want to go to 1400 hertz, that is 1.4 kilohertz. All right. So, it is not an exact multiple of 1000. All right. So, it may be a fraction, or from 1000 we want to come down to 700 hertz. All right. Not exact submultiple 1000 divided by 2, 3 like that. It can be anything else. Then how do you get that? In broadcasting, for example, the frequencies are 32 kilohertz, whereas digital CD, sorry, let me change the pen. Digital CD, it is 44.1 kilohertz. You can see the frequencies are varying so much. And then digital audio tape, it is 48 kilohertz. Then video signals 13.5 kilohertz. This is again for luminescence. In video signal also there are two components that we send. One is luminescence, the other one is a color difference signal. So, color difference signal, that is at 6.75 kilohertz, sorry, this is in megahertz. Even telephony, we normally in a telephonic message we take 8 kilohertz signal. All right. So, music system and telephonic signals, they are not at the same frequency. Music system, you want to preserve different finer components of signals, very high frequencies, different instruments are being played, and in a telephone you just want to get the message, just simple speech frequency is good enough. So, we go for very low sampling frequency. So, there are different signals will have different frequencies, different sampling frequencies. How to put them on a common platform when you require to transmit them in a particular channel or you want to mix them. So, compatibility of signals require that you should be in a position to transfer the frequencies of some signals from one base to another base. Now, before we go to the basics of this change of rate, let us just brush through some of the basic elements of Z transform, okay, that you may be all knowing. I want you to brush up your basics of Z transform. what is Z inverse of 1 by 1 plus Z? You take it as Z inverse 1 plus Z inverse, I can write like this. Okay. So, this is delayed by one step. So, I can write Z inverse of this and then I will give a shift of one step. So, this Z inverse can be kept aside. And what is this? Z inverse of this minus 1 to the power n un. Okay. And that gets a further shift of one step. So, actual output, if I call it yn, will be minus 1 to the power n minus 1 u n minus 1. Is that all right? What will it be? Suppose it is a causal system, then had it been only minus 1 to the power n un, it will be when n is 0 it is plus 1, then minus 1, then plus 1, then minus 1 and so on. And since there is a shift of one step, so actual output will be, this is the Z inverse of this, and multiplied by Z inverse will give me 0, then plus 1, minus 1, plus 1, minus 1, plus 1, minus 1 and so on. Is that all right? Now, suppose it is 1 minus Z squared, 1 minus Z squared, then what do you do? Or for that matter 1 plus Z square, either plus Z square or minus square. Once again I can multiply by Z to the power minus 2 divided by 1 plus Z to the power minus 2, actually Z to the power minus 2 plus 1, it is one and the same thing. Now, I will take Z to the power minus 2 out, I will give at the end shift of 2 steps and determine the Z transform of this, Z inverse of this. So, what will be yn corresponding to this? Let us call it y1n. What is the Z inverse of this? What do you do? Now, if you consider the operation of Z inverse is equivalent to just one shift, then Z to the power minus 2 is equivalent to 2 shifts. Okay. So, treat this as some Z dashed to the power minus 1, where Z dashed is equivalent to 2 shifts, 2 normal shifts I am considering as a single shift in a new scheme. Okay. So, Z dashed is basically Z square, or Z dash to the power minus 1 is basically Z to the power minus 2. All right. So, what will be the result corresponding to this? Could someone tell me? Forget this. What was the result corresponding to 1 plus Z inverse? It was minus 1 to the power n un. It was like 1 minus 1, 1 minus 1. So, the same pattern will be followed with a gap of 2. This gap is now 2 sampling time. Okay. So, I will have 1, this is 1 unit, and so on. Okay. This will be corresponding to this. Do you all agree? So, what will be the Z transform of the whole product? Yn, it will have shift of 2 steps. Okay. So, it will be 0, 0, 1, 0, minus 1, 0, plus 1, 0, minus 1 and so on. Is that okay? Is that all right? Now, let us take z by z square by 1 plus z cubed, z square by 1 plus z cube. What will be the z inverse of this function? I can write this as z to the power 3 if I take out from here and multiply by z to the minus 3, this will become z to the minus 1 divided by 1 plus z to the power minus 3. Is that so? So, corresponding to this, could you please tell me the answer? First will be 0 because it will be finally shifted by one step, and what is the result of this 1 by 1 plus z to the minus 3? It is 1 0 0 minus 1 0 0 plus 1 0 0 minus 1 and so on. Okay. Now, if I have 1 by z to the power minus 3 instead of plus, if I have minus, you know the z transform z inverse of 1 minus z inverse is unit step 1 1 1 1 so on, is it not? So, 1 minus z to the minus 3 will be giving me 1 0 0 1 0 0 1 0 0 1 and so on. Is it all right? In general, we will be having a sequence like 1 0 0 0, at n again it will be 1 0 0, again at 2n it will be 1 and so on, 3n and so on. Is that all right? If it is plus, then it will be alternating in sign. If there is any z to the power minus 2, 3, so many shifts will be there in the intersequence. We will be making use of this property at some stage. So, I just wanted to brush up this. Okay. Now, we call a device which alters the sampling frequency, which increases the sampling frequency by a factor L. Okay. We write like this, an upward arrow. We call this as expander or upsampler, or expander, which expands the signal in the time domain. Okay. So, if you are having x0, x1, x2, x3 like this, a sequence, in the time domain it will be expanded x0, then I push in a few zeros. So, if L is 2, I expand it by 2, that means instead of one segment difference there will be 2 segment gap. Now, this will be x1 0 0, this will be x2 0, sorry, this will be x2, then 0, this will be x3 and so on. Okay. If L is equal to 2, if L is equal to 3, then there will be 2 such gaps, I mean 3 such blocks, that means 2 zeros inserted and so on. So, what will be the mathematical expression for this? I will write x upsampler output, if I call this as x u n, this is x n, x un will be x n by L, okay. N is equal to 0 plus minus L plus minus 2L and so on, and is equal to 0 otherwise. Is this all right? Is this okay? Similarly, we define a downsampler or a compressor or a downsampler like this. Okay. Sorry, M, and this is x n, this side I call it x compressed n. So, this x compressed n will be x n m. I will show it like this. Suppose m is equal to 4, then the first value of downsampler n is the first value of the original sample. First value actually we normally write as 0, 0 is the first value, second value will be x4, next value will be x8 and so on. So, the series that you get here will consist of the values of x, original sequence x, which are occurring at 0, 4, 8 and so on. This is not. So, in downsampler you are actually dropping the values at regular intervals. Excuse me. So, 0, 1, 2, 3, 4, 5, 6 and so on, and suppose these are the values, this is say original analog function, the continuous domain function, and we are sampling it at regular intervals initially at these points. Now, what you are doing in downsampling, you are changing the sampling rate, that means you are taking this point, then again you are taking this point, then again you are taking this point. So, I will darken these, the points that you are picking up when n is equal to 4, it is like this. Obviously, lot of information is lost, because from this point to this point there has been a change, I have missed it out, it is possible. So, we will see very soon what are the restrictions on the rate at which we can downsampling it. We can downsample it at any rate. Now, there has to be some restriction. If you want to retain the informations, then what should be the rate of downsampling? Similarly, do we get anything unwanted if we upsample it? That means a signal is there, it has a certain characteristics, you sample it, you oversample it. Actually, you do not oversample it, you have already sampled, it is already sampled. Now, you are playing with the data by injecting some zeros. You are injecting some zeros, that means you are inserting some values. Is it different from say inserting, suppose I want to expand it by a factor of 2. So, instead of inserting 0, suppose x1 and x2, these are the two adjacent values, I insert a value x1 plus x2 by 2 and somebody else insert a 0, will it be equivalent? So, where is the problem? We would like to see that also very soon. Let me change the pen, it is drying up. Okay. So, x z in an expander or upsampler suppose originally x z is x 0 plus x 1 z inverse plus x 2 z to the power minus 2 and so on, and x upsampler that we are considering, there is a 0 in between. Okay. So, it is a sequence is x 0 then 0 then x 1 then 0 and so on. Suppose you have expanded by a factor of 2. So, it will be 0 into z to the minus 1 plus x 1 into z to the minus 2 plus 0 into z to the minus 3 plus x 2 into z to the minus 4 and so on. So, what is it? X, drop the zeros, instead of z I have actually made z squared, is it not? So, in general, if it is upsampled by a factor of L, then this will be taking the form x z to the power L. Okay. What would be its frequency response? Let us see. This is the discrete frequency in radians. Suppose I am just considering a very simple frequency characteristics. This is your h omega magnitude 0, this is omega c, and this is say pi. It is well within omega, omega c is well within pi, that is the sampling frequency, the Nyquist frequency is covered. Now, I have just doubled it, I have doubled it. What will you get? X z square, if I write x z square and z is equal to j omega e to the power j omega, then what do I get? X e to the power j 2 omega, all right. So, whatever values we are getting at omega c by 2, at omega c earlier, I will start getting at omega c by 2. So, this will be, this base has been reduced to half, all right. But then if I keep on increasing omega, this gets repeated also. So, within pi it will start reappearing also. I have not drawn very good diagram. It will be like this. Suppose it is just pi by 2. If it is pi by 2, so one segment is covered in pi by 4, okay, in pi by 2, then 2 such segments will be covered in pi, all right. So, it will be, let me take this as pi by 2. So, half of this base basically this is from minus pi by 2 to plus pi by 2. So, this is pi. So, it will be somewhat like this. This entire range, this is half the segment, this is half the segment, that makes one full segment, and this is one segment. 2 segments will be covered. If in a range of pi, one segment was covered, now in a range of pi, sorry, once again this will be pi by 2, this will be pi by 2, okay, and pi will be here somewhere, okay. So, it is double. So, till pi, now it is all right, things will start appearing like this. Now, this is the original one, all right, and this is a false image. That means at a frequency within pi, but higher than this frequency, you will have another false contour. What is it due to? Let us see, let us physically understand the actual phenomena in terms of the signal itself. Its original signal is like this. Okay, you have sampled it at this point, at this point, at this point. Okay, so that means your sampled values are these. If I keep on joining them, joining the tips by straight lines even, that will be describing very closely the original analog curve, all right. And now what you are doing by this expander, what you are doing is this one, then a 0, then this one, then a 0, you have inserted a 0 in between. I am just showing it in an expanded form, but basically what you are doing, instead of connecting them, now you are bringing it here and then going up there, bringing it here, going up there. So obviously this function will have an envelope which corresponds to the original analog signal, but it has very high frequency components. That means you are bringing about a very fast change in the signal value. From here it is falling to 0, then again shooting up to a high value. That means there is a very fast change that is taking place, okay, and that will give rise to a high frequency image which has to be got rid of. So if I have a band pass filter, a low pass filter, I will allow only this and drop this, then I can reclaim the original signal. Is that all right? Basically, if you, for example, averaging is a low pass filtering, all right. Suppose I take 3 point average, so this plus 0 divided by 3, then this will be brought up somewhere here. Similarly, these 3 points, if I take the average, it will be brought up here. So if I take the averaging, if I do the averaging of this, then finally I will get something like this, will be somewhat better than the earlier one. It all depends on what kind of filter. Averaging is one kind of filter. I can always have other varieties of filter, where finally we will come back to this profile, all right. If I filter this, it will give me this set of data, will give me an output whose frequency transform, through frequency transform you will find, which will be describing more or less the original analog signal, which was described by this practically. So the image is produced in an upsampler by this upsampling process, and this we will have to see, we have to insert a filter later on. In a downsampler, you are dropping some values, so you are losing some important informations. Now let us see a simple example. Okay, I will take a fresh page. A downsampler, which will be downsampling by 2, and an upsampler by 2, then a delay, I get an output, and the same input is given to another channel where you have a delay, then a downsampler, then an upsampler, and they are added. Let us see what this yn will be like. Okay. let us take this as some x1 sequence, x2, I am writing superscripts, then x3, similarly x4, x5 and x6. Okay. Xn is the sequence x0, I can write like this, x0, x1, x2, it means basically x0, x1, every time I am not putting these braces. So, let me write, suppose x10, then what will be x1n, this sequence, like I have downsampled by 2, so it will be x0, x2, x4, similarly x20, let me stick to the same convention, x10 and x20. What will be x2n? This sequence will be like x0, now I am upsampling it, 0, x2, 0, x4, 0 and finally x10. Okay. Then that gets delayed by one step. So, what will be x3? What will be x3 like? It will be x2n shifted by one step. Okay. So, it will be starting with a 0, then x0, this whole thing is shifted by one step, 0, x2, so this will be a 0, x10 will come later on. I am just observing one particular column, there will be data points on this side also. x4, this one is xn delayed by one step. So, it will be shifted one step. If it is a sequence of data coming, then it will be something like x minus 1, okay, x of minus 1, then x0, x1, x2, x9. Okay. The entire thing has been given a shift. x5 will be x minus 1, then it is downsampled x1, x3 like that, x19, okay, and x6 again filled with zeros. So, x minus 1, then how much is it? 0, x1, 0, x3, 0 and so on. So, x9. Now, if I add x3 and x6, if I add here, what will be the output yn? It will be x minus 1, then 0 and x0, then x1, x2, you will get x9. You will get back the original sequence except for this one shift. Okay. You get the shifted version of the same input sequence. So, they are complementary to each other. Individually, you see there is an upsampler and downsampler by the same factors. There is a delay element, there is a delay element here also, but they do not produce the same sequence. x6 and x3, they are not same. Though I have taken the downsampler and upsampler in the same sequence, same order, I have just changed the positions of these two delay elements and they generate two different sets. That means this entire operation is not linear. It is it is linear, it is not time invariant. In the time domain, they are not invariant. So, it is linear but not time invariant. So, time varying. Both this upsampler and downsampler. Now, let us take for a downsampler now. You have got x mn, sorry, capital M, mn as the output of the compressor, is it not? Every mth value we are considering. So, what will be x compressor z, the z transform of this? Okay, I will not write x right now, it will be x mn z to the power minus n. Okay. Because it is xc n z to the minus n, and xc n is nothing but x original x capital M n. So, it is like this. Suppose you have got x 0, x 1, x 2, x 3 like this. So, x z is x 0 plus x 1 z inverse plus x 2 z to the minus 2 and so on. Okay. And now, you have downsampled by 2, then it will be x 0 next, x 2, x 4 and so on. And so, what is this compressed sequence Z transform? It will be x 0 plus x 2 z to the power minus 1 plus x 4 z to the power minus 2 and so on. Okay. So, what is it in terms of x z? In terms of x z, z what can be what can replace z? Z to the power half. There is something missing, no? So, let us search for that. Okay. Will it be, sorry, you are getting x 2 z to the power minus 2, x 4 z to the power minus 2 and so on. So, z is getting compressed by a factor of 2. So, all right, z will be replaced by z, but will that be sufficient? There is something else missing, all right. So, let us see what this will be like. Let us define a sequence C n as 1 0 0 0 after m steps. If m is the downsampling rate, okay, then after m steps again 1 appears. That is, it is having a sorry, excuse me, it is having a period of m, it is a periodically appearing 1. This is a set. So, I define some intermediate sequence x and as x n into C n, where C n was this sequence. So, basically x n is multiplied by zeros elsewhere, x n is multiplied by at 1 at regular intervals, and this is what is this intermediate sequence. Okay. So, C n can be written, C n can be written as 1 by m sigma W m minus k n. is it not? You have a similar thing we have done earlier. Suppose this is 2 pi and you have divided it by some m number of equispaced points. So, what will be per segment angular shift? 2 pi by m. Excuse me. So, Wm is e to the power minus j 2 pi by m, which you have used in discrete Fourier transforms. So, this is Wm. Let us take m is equal to 8, then what does it mean? 45 degrees spacing like this. Like this, okay. Now, what is 1 by 8 sigma of all these Wms? You can take n is equal to 0, it will be 1, 1, 1, because anything to the power 0 is 1. So, there will be 8 ones divided by 8, so it will be 1, okay. Then if you take n is equal to 1, n is equal to 1 means this will be e to the power minus j 45 degrees 2 pi by 8. I am taking m is equal to 8, say. So, it will be W1, I am not writing 8 every time, W2, W0 is 1 up to W7, and how much is it? 0. All these components, if you add up, it is a balanced set of vectors, so it will be 0. Then if you take n is equal to 2, if you take n is equal to 2, it will be 90 degrees and then multiples of that, so you will get again 0. So, for the next 7 steps it will be all 0, again in the 8th step you will get all ones. This is precisely I was discussing earlier, this is precisely you get in case of a positive sequence, negative sequence components in a 3-phase system. If the system is balanced, then what you get is only 1 when you multiply by alpha square of that balance set, you get 0, okay. So, you get these terms, is it not? 1 plus a square is equal to 0. If I take the double the value of that shift, so 1 plus a square plus a to the power 4, which is again a, that is also 0. So, very similar operation, you take any n point sequence and these values will be always equal to 0, every nth step only it will be appearing as 1. So, Cn can be conceived as this. So, if that is so, then what will be xz, x compressed sequence z, which is sorry, which is nothing but that x intermediate, which is summation of Cn into Xn into z to the power minus n, okay. And what is Cn? I have expressed in terms of 1 by m sigma this. So, I will put it as, this is varying over n, 1 by m sigma Wm minus Kn Xn and z to the power minus n, okay. So, it will be 1 by m sigma, this Wm can be clubbed with Zn x. So, Z and this if I club together, and this to the power minus n gets multiplied by x n. So, original z is replaced by z into this. Okay. Is that all right? So, you take Z transform of x. If you know Z transform of x in a downsampler, you add, suppose it is downsampled by 3, okay. Then whatever xz is given, you multiply z by WMK, all right, where WMK it is sorry, it is summated over k. ZWMK will be e to the power j 120 degrees to the power k. So, z will be replaced by that. You take different values of k, 0, 1, 2, all right. So, 3 such terms will be added together, that will give you and of course divided by 3, that will give you xz. Is that all right? This is summated over k varying from 0 to m minus 1. Okay. So, basically it is a summation of z transforms. If you call it as x1z, x2z, x3z, all right, where I will call it x1. These 3, then what is x1z? It is original xz multiplied by this factor, e to the power j 120 degrees, if I write like this. Next one is x z into e to the power j 240 degrees. Third one is plus x z e to the power j 360 degrees. So, that is xz itself. So, summation of these complex z transforms will be and divided by 3, that will be the overall z transform of xz. Is that all right? What will be its effect? Your downsampling means you are crossing into, probably you are crossing the Nyquist border. That means frequency response, say, which was like this was well within omega s by 2, rather pi, we will call it pi. Suppose I have doubled the frequency, that means this frequency, rather I have downsampled it by a factor of 2. So, this will be going into this, okay, it will be doubled. So, the base will be expanding like this, and then there will be aliasing. So, you can downsample by a factor m such that m times this should be contained in pi. Suppose this is already given as limit is pi by 8, then I can expand it by a factor of 8 when it will be just touching pi. If I downsample it by a factor more than 8, then there will be an effect like this. So, downsampling has this limitation, number 1. Number 2, suppose I have downsampled it by a factor of 4, then this will go up to pi by 2 or 5. If I have gone to 5, then it will be approaching this, and then it will also start reappearing here, and so on. All right. So, we will see what should be the restriction on the rate at which we can downsample, and what are the filters required both for upsampler and downsampler to see that the signal, the change signal carries the original information. That means, the frequency response does not get altered. I will lastly touch upon this point. Suppose I have an upsampler M and then a downsampler, sorry, we are using L and downsampler M. This is an information Xn, I am getting Yn, Y1n. Now, I have a downsampler M first and then L, Y2n. Under what condition both Y1 and Y2 will be identical? Okay. It can be shown that if L and M are mutually prime, if they are mutually prime, they will be identical. Now, I leave it as an exercise. You try at home, take say 2 and a factor of 3, L is equal to 2, M is equal to 3. So, in one case you experiment, you have an upsampler of factor 2 and a downsampling rate with 3, observe Y1. Then you downsample by 3, upsample by 2, observe Y2, upsample by 4, downsample by 6, observe Y3, downsample by 6 and upsample by 4, observe Y4, and then see Y1 is equal to Y2. You verify for yourself whether Y1 is equal to Y2 in this, because this is 2 and 3 mutually prime, whereas with 4 and 6 which one gives you the correct output, that is whether Y3 is equal to these two or Y4 is equal to these two. Then that will decide what should be the order of appearance of the downsampler and the upsampler. Intuitively you can guess, if I downsample first, then I lose out many informations, then packing them with zeros will not really restore the original signal, is it not? I can always infuse some zeros, I can always put some zeros in between, and then I can downsample, some of the zeros will get dropped, some of the other informations will also get dropped. In any case, while downsampling we are doing that, but while upsampling we have expanded the data and then only we are reducing it. It is better to do that instead of doing the downsampling first and then upsampling. But if they are mutually prime, the order does not really matter. So, I would request you to verify all these 4 conditions, 4 outputs. Okay. Thank you very much. We will stop here for today.